We'll start in just a moment. Right, so this lesson I'm going to do on radians and circle sectors, and it's a topic that there's not really much to, but the trick with it all basically is to make sure that you remember the formulae. So with this particular topic, it's practice, practice, practice. So first of all, we'll start off by defining what radians actually are. So the actual definition of a radian is the angle made as follows. So you've got a circle sector, like that. And basically, a radian is the angle made when all three sides of this circle sector are the same. So we've got the radius there, the radius there. So trivially, they are always going to be the same. But also, what needs to be the same is this here. So theta there, but in actual fact, in a circle sector like that, 1 radian is the angle. So it's the angle made by a circle sector where all three lengths on the circle sector are the same. That's 1 radian. Now, if we extend that to think about a full circle, let's think about how many of these there are in a full circle. Well, the formula for the circumference of a circle is 2 pi r. 2 pi times the radius. So to get all the way around the circle here, we times by 2 pi. So 2 pi radians. So therefore, in a full circle, there are 2 pi radians, where that little c means radians. So let's have a look now at converting between degrees and radians. Now, there are formulae for doing this, but I have to admit that I forget what the formulae are. So I'm going to show you as a process of how to work it out. That requires you to remember no formulae. So let's say, for example, I don't know, the question was, e.g., convert 36 degrees into radians. Well, the first thing I'd do is write out the main fact that I know about converting between degrees and radians. Write out that 2 pi radians equals 360 degrees. My target number of degrees is 36. So I can say that I can do that by dividing by 10. So if I divide that side by 10 as well, I get 2/10 pi, or pi over 5 radians equals 36 degrees. Now, it might not be as easy as just dividing by 10. So what we could have done here, we could have divided by 360, then multiplied by 36. So take it down to 1 degree, then push it back up again to 36. So let's do another one. That's converting from radians to degrees now, e.g., convert pi over 2 radians to degrees. Pi over 2 radians to degrees. So do it yourselves. I'll give you a moment and I'll write my answer down in a second. So write the fact down first. So 2 pi radians equals 360 degrees. And our target number of radians is pi over 2. We can divide by 4 to get that. However, let's do it the longer way, just to illustrate that it's equivalent. So find 1 radian, so we're going to divide by 2 pi. Then we want pi over 2 radians, so we times by pi over 2. So we'll do exactly the same at this side, divide by 2 pi, times by pi over 2. Gives 90 degrees. And really, that was more of a role play there, because actually you should know, and we all should know, that pi over 2 is 90 degrees. That's just a key angle that you should remember, much like pi over 4 is 45 degrees. But just illustrating really how these conversions work. One last one, e.g. convert 56.3 degrees into radians. Have a go at that. Then we'll move on. So 2 pi radians equals 360 degrees. And we want 56.3 degrees. So divide by 360 times by 56.3 to get 56.3 degrees. So 2 pi divided by 360 and times 56.3 equals that, or approximately 0.9826 radians. So 563 over 1800 pi or approximately equal to 0.9826 radians. Now, one important thing to point out is that 1 radian is different. So I'll just put a note there. 1 radian is different from 1 pi radian, or 2 radians is a different number to pi radians. So people assume that 2 pi means 2 radians, but it doesn't. 2 radians, or rather 2 pi radians here, is 2 times by 3.14 approximately, much like 1 radian is that there, but this is 3.14 radians. This is 6.48 radians approximately. So just be aware that not all radians have a pi on them, because that's equal to approximately 3.14 radians. I said 6.48, I meant 6.28 radians. And that's just a really important point to remember. So when the answer is 2 radians, don't write 2 pi radians. So let's now apply this to circle sectors. Because when we're working in radians, all of the circle sector formulae that you learned at GCSE, pi r squared times theta over 360, etc., they're made so much easier, but it is another thing to learn, and there's no substitute for just learning these formulae now. So circle sectors and radians, I'm going to put as a subheading. If you want to be copying along with this, fair enough. But I will make the notes available afterwards as well. Circle sectors and radians. Right, so just a rough circle sector there with radius r. And I'm going to call this L. And L is what's called the arc length. And there's the angle theta, which I'm going to measure in radians. And these formulae only work in radians. So radian formulae. So the area of a sector is a half r squared theta radians. And that makes the calculation so much easier and so much shorter if you use that formula. The arc length arc length L equals just r theta when theta's in radians. And that's a real key point there. Learn those formulae. And the best way to learn them isn't just to sit and memorize them. The best way to learn them is to do questions on them and write them out each time a question requires it. Far more productive that you both practice doing the questions and writing the formulae out rather than just sitting there wasting time writing the formulae out without doing any question practice. So we'll take an example question. So let's have a look at this one here. So what I'm going to try and find is the area and the arc length of this using the radians formulae. So we give you a chance to do that, e.g. find area and arc length. And it is just a case of making sure that the angles are in radians, then actually doing it. So see if you can do that. I'll do it myself in a second. So the arc length is r theta. So again, this is good technique for remembering the formula. Just write it out. Equals 12 times pi over 4 equals 3 pi. So 3 pi is the arc length, and the units were centimeters. Probably not so important that you include the units, but we'll do it anyway just to be correct. In mechanics, however, units are very important. And then the area, again, just to aid you remembering these, a half r squared theta, write them out, equals a half 12 squared pi over 4. And I should be able to follow that through my head, but I'm not going to take the risk. Half r squared theta, which is 18 pi. Centimeters squared. Sometimes it's made slightly more difficult. In a question like this one here, because they've actually given you in degrees. So you'll need to convert that into radians first. So I'll give you a moment to do that. But remember, these formulae only work when that there's in radians. You might be tempted on this particular example to just use the degrees formulae, but don't. The purpose of this is to get you familiar with the radians formulae, because in a A-level exam, they are far superior. They save so much time. So even in this instance where it's quicker to use degrees, let's actually go through the process of getting better at turning things into radians as well. So 360 degrees equals 2 pi radians. If I divide by 6, I get 60 degrees. So 2/6 pi. Pi over 3 radians. So pi over 3 radians is the angle. So I want the area and the arc length. Write the formula down to remember it. R theta equals R theta, which is 5 pi centimeters. And the area, well, the area is a half R squared theta. Write it down to remember it. Equals a half R squared theta. Won't try and do that in my head. A half R squared theta equals 37.5 pi. Centimeters squared. And annoyingly, my calculator's in mixed number mode. The way I'm going to change that back, shift, then set up, and go down to fraction result. Now I want it as a top heavy fraction, which is option 2. So hopefully if I press equals there, 75 over 2. Sometimes it's useful to have mixed numbers. Sometimes it isn't. In this case, I think it isn't. So there they are there. So other questions that might be able to, that might try and catch you out are questions like this one, where it doesn't ask you to find the arc length. It asks you to find the whole perimeter. And as I said, these are little tricks that they might try and catch you out with in an exam. So let's have a look at this particular example here. So 2 tricks there that are thrown at you. I'll give you a moment to figure it out, then I'll start. So one of the tricks they've thrown at you is that it's in degrees, but the other trick they've tried to throw at you is that they've actually given you an angle that isn't the one that we need. The sector is the bigger part, the closed part, so we actually need that angle there. Easily done though. 360, take 97. Equals 263 degrees. convert that into radians. 360 degrees equals 2 pi radians. So divide by 360 times by 263. Do exactly the same with this side. Divide by 360 times by 263. 2 pi divided by 360 times 263. 263 over 180 pi. Like that. So now we've got the angle, we can find the perimeter. So the arc length is equal to r theta. Write it out to remember the formula. Equals 8.5 times our angle, 263 over 180. Pi equals I should have just used the answer button there in hindsight. Equals that there. 4471 over 360 pi. And this probably warrants doing an approximation now, because it's quite an awkward number to write exactly. But that's for the perimeter. All we've got currently is this bit here. So the perimeter, we need to add on each of these two radii. Therefore, perimeter equals 4471 over 360 pi plus 2 lots of 8.5 which is equal to 56.02 centimeters. So that's that. So let's have a look at a more problem-based question. So maybe more in an exam context, say. So let's have a look at this one here from an old exam paper. See if we can have a go at that one. I'll go through my solution in just a moment. So quite kindly, the question's guided you to turn 46 degrees into radians. So as always, part 1, 2 pi radians equals 360 degrees. So divide by 360 times by 46 to get 46 degrees. Do it at the other side. So 2 pi divide by 360 times by 46 equals 23 over 90 pi, but it actually asked for the answer to be correct to 3 significant figures. So that's what we're going to do, 0.803 radians. Then find the length of the arc AB. Well, the arc length equals r theta, which in this case is the radius 8 times our angle, which is 0.803. And this is one of the instances where a lot of students will, I've seen before, be tempted to put 0.803 pi, but that's not true. The angle is 0.803, not 0.803 pi, equals that there. So 8 times 0.803. I'm going to use the less precise version than was stored in my calculator, because the question seems to suggest that the number given in part 1, we're going to use that. So that's the reason I've done that. I don't think you'd lose marks either way, though. 6.424. And it was centimeters. Part 3, find the area of the sector. Well, the area, write the formula out, half r squared theta equals a half 8 squared times theta, which was 0.803, so a half times 8 squared times 0.803 equals 25.696 centimeters squared. So a nice straightforward question, but exam questions won't always be so straightforward. So for example, they could ask you something like this. So a question where you're given information, you have to find values, what I'm going to call in reverse. So that one there. The diagram shows a sector AOB of a circle with center O and radius 8 centimeters. The area of the sector is 48 centimeters squared. Find AOB in radians and find the area of the sector bounded by the arc AB and the chord. Sorry, the area of the segment. Key notation there as well, segment, bounded by the arc AB and the chord AB. Now, a segment, do a better job than that. A segment is this bit here. That's a segment. The sector is the whole thing. And that there, a line joining two edges on a circle, or rather joining the edge in two places, that's a chord. Just a bit of terminology there. So see if you can have a go at that question there. So it's told us that the area, which has formula a half r squared theta, is 48. And we know r, a half r squared theta equals 48. Then we can rearrange that. Just 3/2 radians, not 3/2 pi radians, just 3/2 radians. Part 2. Find the area of the segment bounded by the arc AB and the chord AB. Well, what we need now is the area of this triangle. And the formula for the area of a triangle is a half AB sine C, where the angle is C. So this is our angle C here, and there's our sides A and B. Now, one thing that we've got to do, we've got to make sure that our calculator is in radians mode when we're finding sine, cosine, and tangent of an angle. It's important whether we're in degrees or radians as to what mode our calculator's in. So we're working in radians here, so we need to change our calculator to reflect that. So shift then setup, go to angle unit, which is the second option. I'm going into radians. And you can tell whether your calculator is in degrees or radians by looking at the screen. And you can see there, it's in radians. That little R there indicates it's in radians. That would be a D if it was in degrees. So get rid of that. So doing the calculation equals a half A B sine C equals a half A sine 3/2 equals 31.920. So now the area of the segment is our total sector area, 48. Take away what we just found, 48, take away that, which is 16.08. And it was centimeters, so centimeter squared is our unit. So nice and straightforward. And there's worksheets with plenty of those on, and some of my exam questions that I've done on the website or in the live lesson archive area. But what I want to do now, that's pretty much circle sectors and radians. I just want to go through a little bit of practice of solving trigonometric equations in radians, because I think that does catch people out sometimes. So solving trig equations in radians. I want to start off by just drawing the graphs of sine, cos, and tan in radians, just from 0 to 360. So hopefully this is just a refresher. The way I like to draw trig graphs, by the way, I like to actually plot key points first so that everything's nice and to scale. So I'm going to start with sine. And there's the graph there. Oh, a bit of a rubbish bit there. That should be there to keep it to scale, and that should be there. 1 and -1. 0. And normally you'd have got a 90-degree, you'd graduate in 90-degree steps, but we're going to, in radians here, everything's pi over 2, the size of the step. So 1/2 pi, 2/2 pi, 3/2 pi, 4/2 pi. And it helps to try and think in radians. I'm putting the degrees there just for now, but it really helps to start thinking in radians, thinking in pi over 2s rather than in 90 degrees. So there's the graph of cosine. So again, 1 and -1. This time I'm not going to write the degrees equivalent. Start thinking in half pi's. Like that. Actually, I should label these. Y equals sine x. Y equals cosine x. And then for tan, make the graph a bit taller. Now I would always draw the asymptotes in first, because when asked in an exam question to draw the tan graph, if you miss out if the graph crosses the asymptotes, then you would lose marks. So put them in there first so you know the line's not across. So like that there. Across there, right. So it should never touch the asymptote. It should always get forever closer to the asymptote. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. Because those graphs there, you need to know them, and they are useful when solving trig equations. So let's take this example where we're being asked to solve sine of 2x equals 0.2 for 0 between x and 2 pi. Now notice we've got an expression in the bracket here that's more complicated than x. It's a compound trig expression. So what we need to do is change the limits. We're solving this trigonometric equation first of all for 2x. So these limits need to change. So to get from x to 2x, we double it. So we also have to double the limits to 4 pi, and doubling 0, we still get 0. So now let's solve this equation for 2x instead. So if we inverse sine, or as it's known, arc sine both sides, 2x equals arc sine of 0.2, and the calculator will give us that, arc sine of 0.2, and make sure your calculator is in radians mode. What indicates that, at the top of the calculator screen you'll see a little box with an R on, that indicates that it's in radians mode. If that's a D, it will be degrees mode. So arc sine of 0.2 is 0.20136, and we're solving this for 2x. So let's draw the trig graph. Let's find all the other solutions as well. And remember, we're not going from 0 to 2 pi anymore, we're going from 0 to 4 pi. So, drawing the sine graph. Like that. So I've got 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi, 7 pi over 2, and 4 pi. Now if I draw a horizontal line, because we're trying to find where sine x is 0.2, or rather sine of 2x is 0.2, horizontal line, and the solutions we want are here, 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 and here. There's going to be 4 solutions in that range. We know what the first one is. We know it's that there, 0.20136. So all the other solutions for 2x, remember, not for x. So this is actually the 2x axis. And this is the value of sine of 2x here. So we've got 2x equals 0.20136. And we've got pi minus that. So pi minus that answer, 2.9402. We've got 2 pi plus that. So 2 pi plus 0.20136. And just to clarify why I'm adding to some and taking away from some, what I imagine is somebody starting at the beginning of the graph. So a bloke there standing at the beginning of the graph, and to get the first solution, he has to walk 0.20136. So the corresponding person standing at the other side of the hill, because of the symmetry of the hill, has to walk the same distance but in the opposite direction. So it's pi take 0.20136. Likewise, someone starting at the bottom of the hill here has to walk forward 0.20136. Friend at the opposite side has to walk backward 0.20136 to get the solution. So that's why I'm taking from pi here, adding to 2 pi here, taking from 3 pi here. So I'm going to do 3 pi. Oh, I haven't written the solution for 2 pi plus yet. 2 pi plus is 6.485. Or rather, keeping the number of decimal places consistent, 6.4845. And then the final solution, 3 pi take that. So 3 pi take 0.20136. 9.2234. That's still not the answer there. The answers yet, because that is all the answers for 2x. We need to divide them all by 2 now and give them an appropriate degree of significant figures, which I think is going to be, I'm going to use 4 significant figures. Most examples like at least 3, so I'm going to use 4. So divide that by 2. It's in the calculator, so I might as well get 4.612. So 4.612 is the final. Working backwards, let's do 6.4845 divided by 2. 3.242. Next one divided by 2, 2.9402. Quite long these questions can be. 1.4701. And then 0.20136 divided by 2 is 0.1007. And there's our final answers. So do have a go at a few of these on the worksheet. Questions 4 and 7 are the ones to go through.